Carbon and its compounds. Carbon compounds are important in our everyday lives and are found in many common items. Products like toothpaste, soap, cosmetics, medicines, clothes, and paper all contain carbon compounds. Even the food we eat, like bread, is made of carbon compounds. When bread is burnt, the black residue left is mainly carbon. Carbon is found in both living things and non-living things around us. The Earth's crust has a small amount of carbon, about 0.02%. It exists as carbonates, hydrogen carbonates, coal, and petroleum, which are important for energy and industries. The atmosphere has 0.03% of carbon dioxide, which helps to regulate the Earth's temperature through the greenhouse effect. Carbon dioxide is also necessary for photosynthesis. We know that it is a process where plants make their own food, supporting life on Earth. Even though carbon is present in small amounts, it has a huge impact on life, the environment, and various industries. Differences between carbon compounds and ionic compounds. Electrical conductivity. Carbon compounds like methane or ethanol are poor conductors of electricity. This is because carbon compounds do not form ions, means charged particles. Instead, the atoms in carbon compounds share electrons and form covalent bonds. Since there are no free ions to carry an electric current, these compounds do not conduct electricity well, either in solid form or in solution. Whereas ionic compounds such as sodium chloride, that is nothing but table salt, are good conductors of electricity when dissolved in water or melted. This is because ionic bonds involve the transfer of electrons between atoms. It results in positively charged and negatively charged ions. In solution form, these ions are free to move and carry electric charges, allowing the compound to conduct electricity. Next, melting and boiling points. Carbon compounds typically have lower melting points and boiling points. For example, acetic acid, a carbon compound. It has a boiling point of 118 degrees Celsius. The weak intermolecular forces between the molecules in covalent compounds make it easier to break them apart. So, less energy or heat is required to melt or boil the carbon compounds. In contrast, ionic compounds have very high melting and boiling points. Sodium chloride, for instance, has got boiling point of 1413 degrees Celsius. The strong electrostatic forces between the oppositely charged ions hold the ions in a tightly bound structure. This means it takes a lot more energy to overcome these strong attractions and change the state of the compound. Next, forces of attraction. The attraction between the molecules of carbon compounds is not very strong because they are held together by covalent bonds, which involve the sharing of electrons. The molecules interact through weak forces like van der Waals forces or dipole-dipole interactions. This is why carbon compounds are often liquids or gases at room temperature. The forces of attraction in ionic compounds are much stronger. These compounds are formed through ionic bonds, where one atom donates electrons to another, creating positive and negative ions. The strong electrostatic attraction between these oppositely charged ions results in a very stable, rigid lattice structure, making ionic compounds hard solids with high melting points. Bonding in carbon compounds. The atomic number of carbon is 6. The outermost shell has 4 electrons, so its valency is 4. Generally, ionic compounds attain the noble gas configuration by losing or gaining electrons. But carbon cannot do that. Let us see why. If carbon gains 4 electrons, it would be difficult for the nucleus with 6 protons to hold on to 10 electrons. If carbon has to lose 4 electrons, it would require a large amount of energy to remove 4 electrons. It turns into a carbon cation with 6 protons in its nucleus, holding on to just 2 electrons. So, losing and gaining does not work with carbon to make bonds. Covalent bond. Carbon make covalent bonds with other carbon atoms or with atoms of other elements. Before we see the covalent bond in carbon compounds, first study the covalent bond formation in hydrogen, oxygen, and in nitrogen molecules. A covalent bond is a chemical bond formed by the sharing of electrons between two nonmetal atoms. Let us see covalent bonds in hydrogen, oxygen, and in nitrogen molecules. Hydrogen atom has a single electron in its K shell. It attains the nearest noble gas helium's configuration by sharing its single electron with another hydrogen atom. Two hydrogen atoms share their single electrons to form a molecule of hydrogen. Since only one electron is shared by each atom, single covalent bond is formed. Oxygen has 6 electrons in its L shell. It needs 2 more electrons to complete its octet. So each atom of oxygen contributes 2 electrons. That means total 4 electrons are commonly shared by the 2 oxygen atoms. It forms a double bond. Nitrogen. In the formation of nitrogen molecule, each nitrogen atom contributes 3 electrons, means total 6 electrons are shared by 2 nitrogen atoms. Here a triple bond is formed. This is ammonia molecule. One nitrogen atom forms covalent bonds with 3 hydrogen atoms to form this molecule. Here all the 3 bonds are single bonds. This is a methane molecule, CH4. One carbon atom forms covalent bonds with 4 hydrogen atoms. Here also all the 4 bonds are single bonds. Versatile nature of carbon. Carbon is a versatile element. Due to the nature of the covalent bond, carbon is able to form millions of compounds. Let us see the 2 main factors which make the carbon a versatile element. Catenation. Carbon has the unique ability to form bonds with other atoms of carbon. This gives rise to the formation of large molecules. This property is called catenation. Catenation is the self-linking of atoms of an element to create chains and rings. Due to this property, carbon forms large molecules in the form of long linear chains or branched chains and ringed chains. In addition, carbon atoms may be linked by single, double, and triple bonds. Carbon compounds with single bonds are saturated carbon compounds. Carbon compounds with double and triple bonds are called unsaturated carbon compounds. Does only carbon exhibit catenation? No. Many other elements show catenation. For example, silicon. Silicon forms chain compounds up to a length of 7 or 8 atoms. These compounds are very reactive and unstable. Whereas carbon can form compounds with very large number of carbon atoms linked to each other. These compounds are stable because the carbon-carbon bond is very strong. The second factor for the versatility of carbon is its valency. A carbon atom can form bonds with 4 other carbon atoms or with other elements whose valency is 1. Carbon can bond with oxygen, hydrogen, nitrogen, sulfur, chlorine, etc. These compounds will have specific properties. The bond that carbon makes with the other elements is very strong, which makes these compounds exceptionally strong. The reason for the strength of the bonds of carbon is due to its smaller atomic size. Due to the small size of the carbon atoms, the nucleus is close to the shared pair of electrons and it holds these electrons strongly. The bonds formed by elements having bigger atomic size have weak bonds. Saturated and unsaturated carbon compounds. We already learned that compounds with single bonds in their structure are saturated compounds, and compounds with double or triple bonds are unsaturated compounds. C2H6, ethane, is it saturated or unsaturated? Let us draw its structure to know whether it is saturated or unsaturated. First link carbon with carbon using a single bond. Then link 3 hydrogens with 1 carbon and 3 with other. The valency of carbon and hydrogen are satisfied and no double bonds are formed. So, this is a saturated compound. Now let us write the structure of C2H4 ethene. The first link carbon with carbon using a single bond. Then link 2 hydrogens with 1 carbon and 2 with the other. The valencies of hydrogen are satisfied, but the valencies of carbon atoms are not satisfied. Now draw another line between the 2 carbons. Now the carbon valency is satisfied. Now this compound has got a double bond, so it is an unsaturated compound. In the same way, let us draw for C2H2 ethyne. Here we need to draw 3 bonds between carbon and carbon. So this is also an unsaturated compound. Unsaturated compounds are more reactive than the saturated compounds. Chains, branches and rings. Butane C4H10. We can write its structure in 2 ways, like this and also like this. This is a straight chain structure and this is a branched chain structure. But the structure satisfies the valencies of carbon and hydrogen. Both of them have the same formula. We can call these 2 compounds as structural isomers. The compounds with identical molecular formula but different structures are called structural isomers. In addition to straight chain and branched chain structures, some carbon compounds form ring structure also. Such compounds are called cyclic carbon compounds. Cyclohexane C6H12. This is a saturated cyclic compound. Benzene C6H6. This is an unsaturated cyclic carbon compound. So the compounds that contain only carbon and hydrogen in them are called hydrocarbons. The saturated hydrocarbons are called alkanes. The unsaturated hydrocarbons with 1 or more double bonds are called alkenes. The unsaturated hydrocarbons with 1 or multiple triple bonds are called alkynes. Carbon compounds and their functional groups. Carbon can form bond with other elements like chlorine, bromine, oxygen, nitrogen and sulfur and forms new compounds. New carbon compounds are formed when a hydrogen atom of the hydrogen-carbon chain is replaced by an element. The element that replaces the hydrogen atom is called as a heteroatom. For example, here a hydrogen atom of this compound is replaced by chlorine atom. So here chlorine is the heteroatom. These heteroatoms forms the functional groups of the compounds. Sometimes heteroatoms pair up with some other atoms and forms groups. For example, here oxygen is the heteroatom. It forms various functional groups like alcohol, aldehyde, ketone, carboxylic acid. This is chlorethene. Here chlorine is the functional group. This is ethanol. Since OH is the functional group, it is an alcohol. This is acetaldehyde. CHO is the functional group, so it is an aldehyde. This is acetone. CO is the functional group and it is a ketone. The properties of the newly formed compound will be totally dependent on the functional group of the compound. When writing the structure of the functional group alone, the free valencies of the whole group is shown by a single line. Homologous series. CH3OH. This is methanol. It has 1 carbon in it. C2H5OH. This is ethanol. It has 2 carbons. C3H7OH. And this is propanol. It has 3 carbons. C4H9OH. This is butanol and it has 4 carbons. These 4 carbon compounds have OH as the functional group and are called alcohols. Even though the number of carbon atoms in each of these compounds is different, they have very similar chemical properties. Such series of compounds are called homologous series. The series of compounds in which the same functional group substitutes for hydrogen in a carbon chain is called a homologous series. Let us see the homologous series of alkanes: methane, ethane, propane, butane. The difference between each of these compounds is the difference in the number of units of CH2. This is the homologous series of alkenes: ethene, propene, butene, pentene. In alkanes, alkenes and alkynes, we can observe that there is a specific ratio of carbon and hydrogen is maintained. For example, in alkenes, CN-H2N pattern is observed. If N equal to 2, then the compound will be C2H2 into 2, that is C2H4. In any homologous series, we will observe the gradual increase in the molecular mass. If the molecular mass increases, the melting and boiling points also increases. In the same way, the solubility of the compounds decreases with the increase in the molecular mass. That means the physical properties of a homologous series depends upon their molecular mass, whereas the chemical properties of a homologous series solely determined by the functional group. Nomenclature of carbon compounds. The carbon compounds are named on the basis of three things. 1. The number of carbon atoms in the main carbon chain. 2. The type of bonds present in the compound, that means single, double or triple bonds. 3. The functional group present in that compound. The name of a carbon compound is made up of two parts, a prefix and a suffix. Prefix is the first part of the name. It is dependent on the number of carbon atoms present in the carbon chain. If the compound has one carbon, the name begins with meth. If two carbons, it begins with eth, 3 carbons prop, 4 carbons but. If the hydrocarbon chain contains all single bonds, then the suffix becomes ane. This is ethane, methane, propane, butane, etc. If the hydrocarbon chains contains double bonds, then the suffix becomes ene, that is ethene, propene, butene, etc. If the hydrocarbon chain contains triple bonds, then the suffix becomes ine, that is ethyne, propyne, butane, etc. If the hydrocarbon chain has a functional group, the suffix changes according to the functional group. If the functional group of a 3-carbon compound is alcohol, then the suffix becomes -ol, propanol. If the functional group is ketone, it becomes propanone. If the functional group is aldehyde, it becomes propanal. If the functional group is carboxylic acid, it becomes propanoic acid. If the functional group is chlorine, then it becomes chloropropane. If the functional group is bromine, it becomes bromopropane. Chemical properties of carbon compounds. Combustion reactions. Most of the carbon compounds burn in presence of oxygen and produces carbon dioxide. Large amounts of heat and light are released in this combustion reaction. Carbon plus oxygen gives rise to carbon dioxide plus heat plus light. If saturated hydrocarbons like butane, that is cooking gas, is burnt in presence of sufficient amount of oxygen, it gives a clean blue flame with no soot. If the saturated hydrocarbons are giving a yellow flame, it indicates that there is a limited supply of oxygen to that combustion reaction. It leads to incomplete burning of fuel and leads to yellow flame. If unsaturated hydrocarbons like vegetable oils are burnt, yellow color flame is produced with black color soot. In oil lamps, kerosene stoves, firewood stoves, black soot is formed, indicating the incomplete combustion of fuels. Fuels like coal and petroleum contain some amount of nitrogen and sulfur in them. Combustion of these substances releases oxide of sulfur and nitrogen into air, which leads to air pollution. Oxidation. The alcohols, when heated with some oxidizing agents, they get oxidized and converted to carboxylic acids. For example, when ethyl alcohol is heated with alkaline KMnO4 or acidified K2Cr2O7, it produces acetic acid. Here, alkaline potassium permanganate or acidified potassium dichromate adds oxygen to the alcohols and make them into acids. Hence, these substances are called oxidizing agents. The substances that are capable of adding oxygen to other substances are known as oxidizing agents. Addition reaction. Vegetable oils have long unsaturated carbon chains. Animal fats have chains of saturated fatty acids. Unsaturated fats can be converted into saturated fats with the help of addition reaction. When hydrogen is added to the unsaturated fats in presence of a catalyst like nickel, the unsaturated fats turns into saturated fats. This process is called hydrogenation of vegetable oils. Catalysts are substances that cause a reaction to occur at a different rate without the reaction itself being affected. Substitution reaction. Substitution reactions in carbon compounds are single displacement reactions. They occur when saturated hydrocarbons react with chlorine in the presence of sunlight. Chlorine is more reactive than hydrogen atoms, so it can displace them from saturated hydrocarbons. CH4 plus Cl2 gives rise to CH3Cl plus HCl in presence of sunlight. Some important carbon compounds: ethanol and ethanoic acid. Properties of ethanol. Ethanol is a liquid at room temperature. It is an active ingredient in alcoholic drinks. Consumption of these alcoholic drinks is harmful to one's health. It is a good solvent and is used in the manufacture of tincture iodine, cough syrups, and many tonics. Nowadays, ethanol is added to fuel like petrol as an eco-friendly measure. Properties of ethanoic acid. Ethanoic acid belongs to the group of carboxylic acids. It is also called as acetic acid. Carboxylic acids are weaker acids when compared to mineral acids like HCl. 5 to 8% of acetic acid in water is called vinegar. It is used as preservative in pickles. The ethanoic acid freezes at room temperature during winter in cold climate. So, it is called as glacial acetic acid. Reactions of ethanoic acid. Esterification reaction. Esters are usually formed by the reaction between an alcohol and an acid. Ethanoic acid reacts with absolute ethanol in the presence of an acid catalyst to give an ester. Ethanoic acid plus ethanol gives rise to ester in presence of an acid. Esters are sweet-smelling substances. They are used in the manufacture of perfumes and flavoring agents. The esters can be converted back to alcohol and sodium salt of carboxylic acid by treating with an alkali like sodium hydroxide. This reaction is used in the manufacture of soaps and is called as saponification reaction. Soaps are sodium or potassium salts of long-chain carboxylic acids. Reaction with a base. Ethanoic acid reacts with sodium hydroxide to give a salt called sodium ethanoate. Sodium hydroxide reacts with ethanoic acid, gives rise to sodium ethanoate plus water. Reaction with carbonates and hydrogen carbonates. Ethanoic acid reacts with carbonates and hydrogen carbonates to give rise to a salt called sodium acetate, carbon dioxide and water. Now, soaps and detergents. If a shirt with dirt is simply rinsed in plain water, some dirt may go away, but it will not be completely clean because most of the dirt is oily in nature and it cannot be simply washed away by plain water. Soaps and detergents are used to clean the oily dirt. The molecules of soap are sodium or potassium salts with long-chain carboxylic acids. So, one end of the soap molecule is ionic in nature. It is hydrophilic in nature. That means it attracts water molecules. While the carbon chain of the soap molecule is hydrophobic in nature, means it reacts with the oil. So carbon chains hold the oily dirt, whereas the ionic end gets dissolved in water. Thus, the soap molecules are arranged in specific structures called micelles. When the clothes are rinsed by applying mechanical force, these soap micelles help in putting out the dirt and keeps the clothes clean. This is all about carbon and its compounds. Thanks for watching. Please like the video. Please share this video with your friends. Please subscribe to Grade Booster channel.